Welcome to today's Explainer. Have you ever popped the back off a TV remote or maybe looked at the spec sheet of an electric car and wondered what all those random chemical names actually mean? Well, you are definitely in the right place. Today, we're building the ultimate, easy-to-understand study guide breaking down exactly how batteries are classified. We're going to take all those dense scientific definitions and turn them into a super clear, memorable framework that you can take with you.
All right, let's take a look at our source material for today. Yeah, it's a pretty dense wall of chemistry notes, packed with hefty terminology like electrochemical redox reactions and ionic conduction. Our goal right now is to transform this academic text into a really clear visual roadmap that actually makes sense.
Here is our syllabus for this explainer. First, defining the battery. 2. Primary and secondary cells. 3. Comparing battery types. 4. The reserve battery. And 5. Activating reserve batteries. Let's get right into it.
Section 1. Defining the battery, the foundation.
So, at its core, a battery is basically an assembly of two or more galvanic or voltaic cells connected together in series or parallel. The crucial takeaway here is that a battery isn't just some magic box of electricity. It's a very specific, deliberate setup that stores chemical energy, and then, right when you need it, converts that active material into electrical energy via a redox reaction to drive an external circuit. It is quite literally chemistry on demand. Section 2. Primary and secondary cells, the everyday heroes.
To really lock in what a primary battery actually is, I want you to picture a disposable plastic water bottle. You buy it, it's full of water, you drink it, and once it's empty, it's done. You just have to toss it. It has a single one-way life cycle.
These primary batteries give us a continuous supply of electric current straight from their active chemicals. But here is the catch. That supply only lasts as long as those chemicals are present. Once they are tapped out, you cannot recharge it. It's discarded after use. A perfect example would be your standard dry cell, like a zinc manganese dioxide battery. Just one and done.
On the flip side, let's look at the secondary battery. Imagine this one as a really nice, reusable thermos. You drink your coffee from it, but when it's empty, you definitely don't throw the thermos away, right? You just take it to the kitchen, refill it, and it's ready to go all over again.
Also known as accumulators or storage batteries, secondary batteries can actually be electrically recharged after use. If you pass a current through the circuit in the exact opposite direction, you actually reverse the chemical reaction. It totally restores the battery to its original pre-discharge condition. That's exactly what's happening inside a lead storage battery or a NiCad battery every single time you plug your device into the wall.
Section 3. Comparing battery types, the showdown.
Looking at them side by side, it all really just comes down to the dividing line of reusability. Primary cells are single-use, discarded, and rely on an irreversible reaction, like that dry cell we mentioned. Secondary cells are rechargeable, driven by a reversible current, and designed for multiple life cycles, like your lead storage or NiCad. It 100% depends on whether that fundamental electrochemical reaction can run in reverse.
Section 4. The reserve battery, the outlier.
Now think about this for a second. Standard batteries, even when they aren't plugged into anything at all, just slowly lose their charge sitting there. The chemicals are always kind of reacting. So what if you have a device that absolutely has to sit on a shelf for, say, a decade, but the exact second you need it, it has to deliver maximum power flawlessly? That is a massive engineering problem. How do you stop those active materials from slowly degrading over all that time?
Well, the answer is the reserve battery. And honestly, the best way to visualize this is to picture a glow stick. A glow stick just sits perfectly inert in your drawer for years, right? It doesn't do a thing until you physically snap it, break that inner vial, and mix the chemicals together. Only then does the actual reaction kick off.
The mechanics behind how it pulls off that glow stick trick are super fascinating. In a reserve battery, a key component, which is usually the electrolyte, is physically separated from the rest of the cell until right prior to activation. By totally isolating that electrolyte, these batteries basically eliminate any chance of self-discharge, and they minimize chemical strength loss. Much like primary cells, they are mostly single-use. Some common examples include aluminum and silver zinc batteries.
Section 5. Activating reserve batteries, the mechanics. So how exactly do you snap the glow stick when the battery is sealed deep inside some complex machinery? Let's look at a specific type called a thermal battery.
It goes through this really elegant step-by-step physical transformation. Step 1, the electrolyte is isolated in a solid state. Step 2, when the battery is needed, heat is applied until that electrolyte reaches its melting point. Step 3, as it turns into a liquid, ionic conduction finally becomes possible. And boom, Step 4, the battery is fully activated and provides full power.
Because of this wild activation process and their crazy long shelf life with zero power loss, these batteries are trusted for some incredibly extreme one-shot applications. We're talking missiles, torpedoes, timing devices, and temperature or pressure-sensitive detonation devices. Basically, weapons systems where, oh, the battery died in storage is absolutely not an acceptable excuse.
And that brings us to the end of our explainer. I really hope this study guide has completely demystified how we categorize primary, secondary, and reserve cells for you. So I'll leave you with this. The next time you pick up a device, ask yourself, what kind of invisible chemical reactions are powering your world right now? And were they engineered to last a lifetime, or just burn bright once? Thanks for hanging out, and keep learning.